So last class we talked about Taylor series and how to find them, and we had a formula that involves the function f and all of its derivatives being evaluated at the center, which is often 0, right? Not always, but it's the most famous way to do it. So these are 6 famous Taylor series. All of them I've centered them at 0. We've derived all of these either in class or as a homework exercise. So these are 6 Taylor series that you should be familiar with. Maybe write them on your cheat sheet for the test. So today we're going to explore Taylor series a little further. And the process that we've seen for getting Taylor series is cumbersome. It involves taking many derivatives, which can be cumbersome. So we have some alternatives where we can manipulate or sort of adjust the series that we've already found. So one thing we could do is substitute into an existing Taylor series. So if I wanted to have a formula for e to the x cubed, I could just plug in x cubed into my Taylor series for e to the x. So e to the x cubed would be, everywhere I see an x in there, replace it with an x cubed. So I'm going to have 1 plus x cubed over 1 factorial plus x cubed squared is x to the 6th over 2 factorial. X cubed cubed is x to the 9th over 3 factorial. And x to the 4th cubed would be x to the 12th over 4 factorial. And then we're done. So this saved us from having to take many derivatives of e to the x cubed. All right, so what if I wanted to do the ln of 1 minus 2x? If you start with the ln of 1 plus x, what should we plug in there into every x value to get the ln of 1 minus 2x? Negative 2x, yeah, because this is the ln of 1 plus negative 2x, right? So instead of 1 plus x, it's 1 plus negative 2x, and you throw a negative 2x in for x everywhere in the series for ln of 1 plus x. So we would have negative 2x minus negative 2x squared is positive 4x squared over 2. And I might have to simplify my fractions when I'm done. Okay. And then I would have a plus, but I'm going to be cubing a negative 2x, which is going to give me a negative 8x cubed over 3. And then I have a minus. And I'm going to raise negative 2x to the 4th, which becomes positive. And 2 to the 4th is 16x to the 4th over 4 minus dot, dot, dot. So that's one way to generate a Taylor series without having to go through that whole process of finding derivatives and plugging it in and putting it into the formula. Another thing you could do is use multiplication or division. If I wanted to find the Taylor series for the function x squared times the ln of 1 minus 2x, it would be quite cumbersome because the derivative, to take the derivative of that, I'd have to use the product rule. And undoubtedly, I'd have to use the product rule plus some other rule in the second derivative. But I have a Taylor series for the ln of 1 minus 2x that I just found up here. So I'm just going to take x squared and multiply by this series. Negative 2x minus 2x squared minus 8x cubed over 3 minus 4x to the 4th. And just distribute your x squared. So I have negative 2x cubed minus 2x to the 4th minus 8x to the 5th over 3 minus 4x to the 6th over nothing. Don't need a parenthesis there. So you can multiply things together to get a new series. Sine x over x, right? So we could divide. Take your series for sine x and divide the whole thing by x. And then you can take that x and divide it into every term. Okay, so we're going to end up with 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. Right, so it's just dividing by the x is going to reduce all your exponents by 1. So one of the huge reasons that we teach Taylor series in Calc 2 rather than Calc 1, even though you could do it in Calc 1 because it just involves derivatives, is that it makes integration easier, right? Differentiation, but also integration, because integration is hard, right? Finding antiderivatives is hard. So a few classes ago, we used a Taylor series to find the integral from 0 to 1 of sine x over x. And I think in this particular class, we actually didn't finish that. So maybe I'll do that first, and then we'll come back to the other thing. So if I want to find the integral from 0 to 1 of sine x over x, well, the Taylor series for sine of x centered at 0. Oh, actually, we didn't use the series. We used a Taylor polynomial. The entire series, right, is going to, so I'm going to have the integral from 0 to 1 of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. There's sine x all over x dx. And then you divide the x in like we just did. So we're going to have 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus dot 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 dx. And now this guy is easy to find an antiderivative for because it's just a polynomial and we can just use the power rule. So the antiderivative of 1 is x. And then x squared, its antiderivative is going to be x cubed over 3. Antiderivative of x to the 5th is x to the 5th over 5. And antiderivative of x to the 6th is x to the 7th over 7. And I got to take that whole thing and evaluate it from 0 to 1. All right, so if I plug in a 1, I get 1 minus 1 over 18. 1 over 5 factorial is 120 times 5 is, yeah, minus 1 over, okay, now I can't. I should probably learn the factorials, like up to 10. Oh well. Okay, so 7 factorial times 7 is 35,280. And then my next one will be 1 over 8 times 8 factorial. Oops. $322,560. So that's what I get when I plug in 1, and then I got to plug in the 0, right? Fundamental theorem of calculus. But that's just going to give me 0 because every term has an x in it. So now I'm left with an infinite series. The terms are approaching 0. They're getting smaller, going towards 0. The signs are alternating, which means it definitely converges. What does it converge to? It's not geometric. Any ideas? I don't think we actually have any way to figure out what it converges to, but we could estimate by chopping it at any point, right? We could get an estimate for the area under that curve. So it's approximately equal to 1 minus an 18th plus a 600th minus that would be an approximation for the area under sine x over x from 0 to 1. Oh, sorry, we weren't done. Okay, so that makes integration easier. We can also find the 12th derivative of e to the x cubed. So we should start with the series for e to the x cubed. We wrote it down on the previous slide. Okay, so here's my series for e to the x cubed. Let's think about what would happen if I try to take the 12th derivative. So all of the terms that have a degree less than 12 are going to eventually hit 0, right? Because every time you take a derivative, the exponent is going to reduce by 1. So if I want to take the 12th derivative, all of the terms whose exponent are less than 12 are going to drop out. So maybe I should add a few more terms here to go past the 12th. Oh, right, okay. So my next one would be x to the 15th over 5 factorial, x to the 18th over 6 factorial. Okay. All right, so what happens to my 12th degree? When I take 12 derivatives of it. The 1 raised to the 12th. Yeah, the x to the 12th over 4 factorial. So all of these guys, when I eventually is going to come to be like, eventually I'm going to bring down a 1 and the exponent's going to be a 0. So that term's going to be a constant and its derivative will be 0, right? So all of these guys whose exponents are less than 12, when I take 12 derivatives, I'll eventually just get 0, right? So if you have any polynomial like x to the 5th, right? When I take derivatives, I get 5x to the 4th, 20x cubed, 60x squared, 120x, 120, 0. Right? So eventually, any power function, when you keep taking derivatives, will eventually give you 0. So if I'm going to take 12 derivatives, if my exponent is less than 12, I'm eventually going to get 0 for the derivative. But what about when the exponent is 12? Let's think about the x to the 5th. How many derivatives did it take me to get down to 0? 1, 2, 3, 4, 5, 6, 0. 6 derivatives got me to 0. So for x to the 12th, it would take 13 derivatives to get me to 0. But I'm only taking 12, which means I'm just going to get to the constant. I'm just going to get to the constant when I take 12 derivatives of x to the 12th. Okay, so I have to figure out what that constant is. What do you think it's going to be? It's going to be 12 factorial, yeah. Because I'm going to bring down the 12, then I'm going to bring down the 11, and then the 10, and then the 9, and then the 8, and it's going to go out to 1. And you're going to get x, it'll be 12 factorial times x to the 0 over 4 factorial. All right, what's going to happen when I take 12 derivatives of x to the 15th? It's going to be quadratic. How come? So you're saying x cubed. Yeah, so yeah, if I take 12 derivatives, each time I take a derivative, it's going to reduce the exponent by 1, right? So 15 minus 12 reductions would be an x cubed. So I'm going to be left with an x cubed. But then what number is going to go in front of that? Yeah, it's going to be 15 times 14, blah, 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 down to 3. Yeah. Actually, it's going to stop at 4, right? Because the 3 never got brought down. I don't think it's minus. Yeah, so yeah, it's 15 times 14 times 13 times all the way down to 4, right? And 15 factorial would go all the way down to 1. So maybe it's over 3 factorial, because then that would cancel with that. Yeah, so not minus, but divided by. Yeah. So it's 15 factorial over 3 factorial. All right, and then the x to the 18th. I'm going to take 12 derivatives, which is going to leave me with x to the 6th, right? All right, so I'm going to have an x to the 6th over 6 factorial. And then my coefficient would be like 18 factorial, but it's going to stop at 7, right? Because I'll never have brought this 6 down. So it's going to be 18 factorial over 7 factorial. Yeah, over 6 factorial. Thank you. All right, we'll do one more term. So that's going to be x to the 21st. So when I take 12 derivatives, I'm going to have x to the 9th left. And it's going to be like a 21 factorial in front. Sorry, that's a 7 factorial. Okay, but the factorial, 21 factorial, is going to stop at 10, so I would have to divide out a 9 factorial. Whew. So there's my 12th derivative of e to the x cubed. I'm sure I could simplify. I don't really want to. All right, so when you differentiate a Taylor series, the radius of convergence stays the same. So here's a function from our list of famous Taylor series. The series for 1 over 1 minus x is 1 plus x squared plus x cubed plus x to the 4th, etc. Right? Its radius of convergence is -1 to 1, because 1 plus x squared is a geometric series, right? Where the multiplier is x. And so this only converges when the absolute value of x is less than 1, which means between -1 and 1. So it only converges for those x's, and it converges to the first term over 1 minus the multiplier, 1 over 1 minus x. All right, so if I was going to take the derivative of that thing using Calc 1 techniques, I would say, okay, first thing I'm going to do is probably rewrite 1 over 1 minus x to 1 minus x to the -1 so that I could apply the power rule. All right, and then the power rule says bring the -1 down in front. and I'd have 1 minus x to the negative 2, but then I still have to do what? Multiply by the derivative of the inside, which is the chain rule, and the derivative of the inside is negative 1. So this comes out to positive 1, because we got a negative 1 and a negative 1 over 1 minus x squared. So now if I wanted to find it using Calc 2 techniques, I would take the derivative of the series. So if I want to find d dx of 1 minus x, I would take the derivative of the series. So that's 1 plus x squared plus x cubed plus x to the 4th. So the derivative of 1 is 0. And then the derivative of x is 1. The derivative of x squared is 2x. There's my series. Okay, so those two answers don't immediately look the same, right? So we got to do a little bit more work to show that this is the series for this. Okay, so 1 minus x times 1 minus x. If I was going to do it via series, right? Because that is 1 over 1 minus x squared, right? That's the derivative we found. So if I were to try to multiply that out, so 1 over 1 minus x times 1 over 1 minus x is this series times that series again. And hoping that we will show that when I do that multiplication, that's the series I'm going to get. The derivative of 1 over 1 minus x. Okay, so how can I go about doing this sort of infinite multiplication? So maybe a simpler question to start would be like, how do you multiply more than two things, right? So all the time, don't ask me why, maybe because it's quick and easy. You see, you know, problems like that, and you have this thing called FOIL, right? And it's first, outer, inner, last, and you go, okay, so that's 2x squared plus 4x minus 4x minus 8. Right? And then you combine like terms and whatever. What if I asked you to multiply three things together? You multiply every term by every other term. There's no special acronym for it. I kind of hate that we teach FOIL because it makes people think that you can't do it with bigger polynomials, but you just multiply every term by every other term. So do it systematically so you don't lose track of what you're doing. Start with the x squared, distribute it to every term in the next parentheses. Then you move to the x, distribute it to every term in the other parentheses, and then the -3 and distribute it to every term. So I'm going to start with my 1, and I'm going to distribute it to, I can't do it to every term, but I'll just do it to the first several. So when I distribute my 1, I get 1 plus x squared plus x cubed plus x to the 4th. And let's say that's enough, right? Then when I distribute my x, I get plus x squared plus x cubed plus x to the 4th, x to the 5th. And then when I distribute my x squared, I'm going to get x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th plus. So now if I start to try to combine like terms, you see each time I distribute a term from the first series, my first term goes up a power. So like my only constant term is already written down, and it's a 1. And my only x terms are here and here. So I have a 2x. And then my only x squared terms are here and here and here. And my next thing I distribute is going to be an x cubed, which means I will have no more x squared terms. So I have 3 x squared terms. And then my x to the fourths, I have 1, 2, 3. I'll have another one in the next one, and another one after that, because I'll be distributing an x cubed and then an x to the fourth. So I'm going to have 5 of them. And that is the series that we came up with for 1 over 1 minus x squared. That's the derivative we came up with. And we just proved that that is... Oh, I messed up. Sorry, I skipped the x cubed terms. Skipped the x cubed terms. I'm going to have 1, 2, 3, 4 of them. That is the series we came up with for the derivative of 1 over 1 minus x, which we know from Calc 1 is 1 over 1 minus x squared. Put that sentence down there. Okay, so in part of your reading this year, you might have encountered the sine integral. If you did your reading? It's called psi of x. And it's a function where you plug in an x value, and it's an integral from 0 to that number you plugged in of sine t over t. So it's like a cumulative area function. It measures the area under sine t over t from 0 to any number you put in. So apparently some engineers and scientists use this function a lot, especially in optics. Let's come up with a Taylor series expansion of psi of x. So I already have a Taylor series expansion for sine t over t. Right? I did that, I don't know, a little earlier. Sine x over x. 1 minus x squared over 3 factorial. Okay, so there's my function for sine t over t. I had it for sine x over x, just replace the x's with t's. So now what I want to do is find psi of x, which means I want to integrate this thing from 0 to x. So the integral from 0 to x of 1 minus. So first I need an antiderivative, then I got to plug in an x, then I got to plug in a 0 and subtract them. So first antiderivative. The antiderivative of 1 is t, because my variable, I should have a dt there, sorry. My variable is t, so working with t, so my antiderivative of 1 is a t. And the antiderivative of t squared is t cubed over 3. And the antiderivative of t to the fourth is t to the fifth over 5. T to the seventh over 7 times 7 factorial. And then I have to evaluate all that from 0 to x. So first we plug in an x. Replace all the t's with x's. So this is, just a mindless task here. Oops. Okay, then I got to plug in a 0. And what do you get when you plug 0 in here? 0. So that is your psi of x function in a Taylor series expansion for this thing that we were unable to define. We could only define it in terms of an integral, right? It was this thing, the integral from 0 to x of sine of t over t dt. It feels really complicated, but now it's just a polynomial, just an infinite polynomial, easy to work with. Okay, so now we're going to derive a formula for e to the I theta, which leads to the absolute most awesomest of equations in all of math. We did this for just a single theta last class. We did it for 2 pi. So I'm going to start with my formula for e to the x, which is 1 plus x squared over 2 factorial. That should be enough. And then I'm just going to replace all my x's with I thetas. Oops. All right, so raising I to a power, there's only 4 possible answers, and it goes I, negative I, negative 1, negative I, 1. I, negative 1, negative I, 1. So my first one's an I. So this ends up being 1 plus theta times I. And then when I square this I here, I'm going to get I squared, which is negative 1. So that's just going to change my sign. And I'm not going to have any i's left. I'm going to be left with theta squared over 2 factorial. And then I cubed is going to be negative I. So my sign's going to be negative. And I'm going to have a theta cubed with an I still over 3 factorial. And then I to the 4th is positive 1. So this just becomes plus theta to the 4th over 4 factorial. I to the 5th is I. So this is theta to the 5th times I over 5 factorial. I to the 6th is negative 1. So this is negative theta to the 6th over 6 factorial. So all I was doing was simplifying my I to a powers. Now collect everything that has an I. Maybe I won't bother writing it all out since we've done this. Stuff without i's is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. That is the Taylor series for cosine theta. Okay, and then things that have i's in them, I have theta times I minus theta cubed over 3 factorial times I plus theta to the 5th over 5 factorial times I. And if you ignore the i's, that's the Taylor series expansion for sine theta. But all of them are multiplied by I, so this is plus I times sine theta. So we have e to the I theta is equal to cosine theta plus I sine theta, which means that e to the 2 pi I is cosine 2 pi plus I sine 2 pi, which is 1.
Somehow related to that series of programs. Somehow related to that.
It converged to pi squared over 6,
Yeah.
1 over n squared. That's a good question. That's a very good question. So I'm just going to guess at what triggered that connection for you is that e to the I theta, how on earth is it related to cosine and sine, which has to do with circles, which have to do with pies, right? And then we had this other thing where this thing that seemed completely unrelated to circles and pi ended up being pi squared over 6. So that ended up having a surprising connection to circles also. I don't actually remember the proof for that off the top of my head, so it might have something to do with that formula. I don't remember. Okay, so I'm going to have you try some. Find the Taylor series expansion for each function about x equals 0. You shouldn't need to use repeated differentiation, right? You shouldn't have to take multiple derivatives, plug in 0, and go into the original formula for a Taylor series. Start with a Taylor series you know and like manipulate it to get the one that you want.